the frequency response of MOS amplifiers. We also spoke about the parasitic capacitors, the various parasitic capacitors in a MOS device, and their impact on the frequency response of the MOS amplifiers. We started with our analysis on a simple common source amplifier, and we said when you include the gate to drain capacitance between the input and the output terminals, the mathematical analysis becomes much more complicated. And we said we are going to make some simple approximations using Miller's theorem and derive the poles and zeros for the system. So we said this capacitance CGD using Miller's theorem, which says that if you have an impedance between two terminals and we have some third common terminal, then it can be split and represented as two impedances between the two terminals, between the input, as two independent impedances, one at the input and one at the output terminal. So this makes these two nodes non-interacting. And the value of this capacitance, or the value of this capacitance CGD reflected at the input port is given by CGD into 1 plus GMRL, where GMRL is the gain of this amplifier. And at the output port, it can be modeled as CGD into 1 plus 1 by GMRL. And this directly follows from the Miller's theorem. We said that by doing so, we can then reduce the circuit to something of this form, where you have one capacitance at the input port and one capacitance at the output port. So you have C1 and C2 at the input and the output ports. Now to analyze this circuit, it's much simpler than the previous circuit. Now we can instantly notice that the gate current drawn into the MOSFET is 0. So because there is no CGD, there is no current drawn into the MOS or into the amplifier to the output now. So I can analyze this part of the circuit separately and the MOS amplifier with a resistive and capacitive load separately. So now when we have a circuit like this, we go with the standard procedure. We first find the DC gain, then the poles and zeros for the circuit. Then we can readily write the transfer function. The DC gain of the circuit is, we find that by open circuiting the capacitors. So this input node voltage will come to Vi. So the output node voltage will simply be minus of GMRL times Vi. So the gain here is simply minus of GMRL. That's the DC gain of this amplifier. The next goal is to find the poles and zeros. I'll first start with the zeros. A zero, by definition, we said even when the input is present, the output should go to 0 at that value of S or omega. Now we can see here that there are two possibilities. One, the output impedance should go to 0, should vanish to 0 at some frequency, or this node voltage can go to 0 at some frequency. And we can see because there are capacitances at both these nodes, at infinite frequency, at omega equal to infinity or S equal to infinity, capacitors offer 0 impedance. At that condition, both these nodes will go to 0. So therefore, we can say there are two zeros in the system and both these zeros happen to be at S equal to infinity. So since they are not in finite zeros, we won't be showing them on the transfer function. The next is to find the poles of the system. To find the poles, there are two conditions again. We can use the condition where the output impedance blows up to infinity. If output impedance blows up to infinity for some value of S, then the output voltage will also blow up to infinity. So that we already discussed how to find that. If you have a parallel RC circuit, simply equate the 1 by SC, or you equate the impedance of the capacitance to be equal to the negative of the impedance of resistance. From that we get the pole as minus of 1 by RLC2. The other pole will be at the input port, and that can be easily found. Again, this is an RC circuit. It's a simple low pass RC circuit. We said in such a circuit, when RS becomes equal to minus 1 by SC1, at that point the current drawn from the input will be infinity, because the series of RS and C1 is 0. It offers a 0 impedance at that value of S. So current becomes infinity. So if an infinite current flows into a capacitor, the impedance of the capacitor is finite at that value of S. Only a DC capacitance impedance is infinity. But at this value of S, S equals minus 1 by RSC, when the impedance is finite. So finite impedance and an infinite current flows through that, so the voltage will become infinity. So this was the other condition. So we get the pole expression as minus of 1 by RSC1. So now we know there are two capacitors, and we said at max we can have 2 poles and 2 zeros, and we saw the locations for both the zeros at infinity, and the pole locations were also found. So the transfer function reduces to something like this. You will have 1 plus s rs c1 into 1 plus s c2 rl. So the plus sign indicates they both are left of plane poles. Now the value of c1 includes the gate to source capacitance of the device, the CGS, plus the Miller reflected capacitance due to CGD. So CGD into 1 plus GMRL. The value of C2 on the other hand will include the load capacitance. This is the load capacitance that comes with the load, plus the gate to drain capacitance from Miller's theorem. So this will be CGD into 1 plus 1 by GMRL. So Miller capacitance, the reflected capacitance seen at the output node. I can also include CDB, the drain to bulk capacitance here, but I can absorb all of that into the load capacitance and simply call it CL. Now what happens because of this is that even though I'm going to assume CL is much greater than CGS and CGD, this is the assumption I'm going to make. Had there been no CGD, I can, because CGS is also very small, I can see the system as though having a single pole. So if I take this transfer function, I can neglect C1. C1 will be very small if there was no CGD. Then the gain will simply be minus of GMRL by 1 plus S C2RL. So C2 will be just CL itself, it will be CLRL. And that's the frequency response of that function is shown in yellow here. Now if I include C2, we end up getting 2 poles. And I'm going to make another assumption that your RS is really large. Now what does RS tell us? We said any voltage source can be modeled, a practical voltage source can be modeled with a series resistance in series with it. And this series resistance captures the maximum power delivering capacity of this voltage source. A voltage source with a resistor in series tells us the maximum power that this voltage source can deliver is Vs square by 4 Rs. So that's what a large RS simply means, that this voltage source can deliver very little power. Now in such a case, I'm going to get 2 poles. One will be at 1 by Rs C1, the other one will be at 1 by RL C2. Since I assumed Rs to be much greater, a really large value, the pole due to Rs C1, that will come first. That will be a lower frequency pole compared to the pole which is at 1 by RL C2. Now you can see here from this equation, C2 is equal to CL plus CGD into 1 plus 1 by GMRL. Since CGD is a very small value and since the gain is a really large value, I can approximate this to CL plus CGD, and since CGD is much smaller than CL, I can approximate this to CL itself. So that's why I haven't shown the second pole changing much. I've written it as 1 by RL C2, but this I can approximately call it as 1 by RL CL as well. It's the same as before, very close to what it was before. But now you can see here a new low frequency pole is introduced, and that is reducing the bandwidth of your amplifier. So previously the bandwidth was 1 by RL CL, now it has reduced to 1 by RS C1. This is because of the capacitance CGD, and we used Miller's theorem. So this capacitance CGD appears as a really large capacitance at the input. So this capacitance multiplication effect is what we call Miller effect. So common source amplifiers suffer from Miller effect. We will later see when we discuss cascade amplifiers how we fix this problem. But this is the problem with a common source amplifier. Now one good thing about Miller's theorem is that it enables us to solve the circuit quickly and get a reasonable approximation of the actual frequency response of the circuit by using a simplified version of the circuit. So we get the frequency response of this circuit very similar to this one, but we are making an approximation here. So I'm splitting this capacitance into 2 capacitors here and analyzing it. The analysis became much simpler, but we are missing out something in this analysis. And that something is your right of plane 0 because of CGD. To show that you will have a right of plane 0, I'll analyze it in the standard procedure we were discussing some lectures ago, is that we will first find the short circuit transconductance and we will find the output impedance. Then the product of short circuit transconductance GM of S into Z out of S will give us the voltage gain as a function of frequency. So first I'll find the short circuit transconductance. So I'll short circuit the output and measure the current flowing here. Now you can see at the input port you have VI, RS, and both these capacitors are to ground. So you get CGD plus CS. So the voltage at this node, we can directly say it is VI. So it's a simple low pass RC circuit. So by now we know what the transfer function is. It is 1 by 1 plus S into this capacitance. So that's what I've written here. That's the node voltage Vx. Once you know the node voltage Vx, finding the short circuit current is pretty trivial. So you have a capacitance CGD here. So this node voltage is Vx. So you have GMVI is the current through the MOSFET, and this is Vx. Vx into S CGD is the current through the capacitor. So the total current ISC is given by minus GMVx plus Vx into S CGD. So I've taken minus GMVx common out. You will get minus of GMVx into 1 minus S CGD by GM. So from this I get the short circuit current as minus of minus of GM into 1 minus S CGD by GM and divided by 1 plus S CGS plus CGD into RS. Now the same way we can calculate the output impedance, which will be a little bit more complicated, but what we can show, I have not explicitly shown here, is that this pole will get cancelled out. You will have a 0 in the output impedance, and that will cancel out this pole, but this 0 will remain. You have a right of plane 0 given by GM by CGD, and this 0 doesn't show up when we do this Miller approximation. That's the drawback of the Miller approximation. It doesn't really show us the 0 present in the circuit. At a later stage, I'll carry out a more rigorous analysis of a common source amplifier with CGD. But for now, this suffices. This gives us a good understanding how to apply Miller approximation and what is missed in the Miller approximation. You don't predict the 0 in the Miller approximation. Now I'll discuss a common source amplifier. To finish our discussion on common source amplifiers, I'll discuss a common source amplifiers with source degeneration. And this analysis is very useful, especially when we are analyzing differential pairs. So that's why I thought I'll spend some time analyzing the frequency response of this circuit. We have already analyzed a circuit when we were, this circuit especially, when we were trying to find out poles and zeros intuitively. But here we will plot its frequency response and have a look at it, how the response looks like. So I'll quickly revise what I did in the previous lecture. So that is, we quickly found out the poles and zeros for the circuit. So any circuit, the first step is to calculate the DC gain. So for this, the DC gain is pretty simple. It's a source degenerated MOS device with RL being its load resistance and RS being its source resistance. And the DC gain is given by minus of GM RL upon 1 plus GM RS. This is the DC gain of this amplifier. Now we'll first find zeros. We said to find the 0 if this impedance blows up to infinity. If this impedance blows up to infinity, then your current becomes 0. So here I have assumed lambda is 0, which is R0 is infinity. So at this point, if this impedance becomes 0 at some value of S, then the current flowing through this MOSFET becomes 0 because your source node is floating, the current here is 0. That's the same as drain current, which becomes 0 as well. So all we need to do is find out the point where this impedance blows up to infinity. That happens when RS becomes equal to minus 1 by SCS. So the 0 will be minus of 1 by RSCS, which is a left of plane 0. The other condition is to find the pole. So one pole is directly at the output because you have RL and CL in parallel. So that impedance can blow up at 1 by RLCL I mean, since it's left off plane pole, write it as minus 1 by RLCL. That's where the transfer function blows up to infinity. So there is one pole there. There is another pole. Right now I'm ignoring RL, the RLCL, and we found this other pole using the short circuit transconductance. What we did was that we removed the load resistance, and we found, by applying an input, we found the condition when your current blows up to infinity. So now the transconductance is given by Gm by 1 plus Gm Zs of S. So we just had to find out the condition where this goes to 0, which is Zs of S equals minus 1 by Gm. This was the condition for pole. So solving this, we got this equation for pole as minus of 1 by Cs into Rs parallel 1 by Gm. So now we have all the poles and zeros. So this is your minus of Gm RL by 1 plus Gm Rs. The 0 is at 1 plus RSCS, SRSCS. Since it's a left off plane 0, I have written plus here. And we found the two poles. One pole is the output pole, which is 1 plus SRLCL. And the other term shows the pole where your short circuit transconductance blows up to infinity. And that also happens to be a pole in the system. I'll first plot this graph assuming CL is 0, because it's much simpler and we can look at some very interesting results here. I'll first assume CL is 0. If CL is 0, here the transfer function in the circuit, so this I can ignore this term. I can ignore this term here. CL is 0. So I have just one pole and one 0 and one pole. Now we can analyze the circuit intuitively as well. So we have a scenario like this way. So you have Rs and a capacitance Cs, and I've ignored CL right now. So the circuit reduces to something like this. Now I'll find A of 0. The DC gain of the circuit is simply Gm RL by 1 plus Gm Rs. So that's the DC gain here. And at infinite frequencies, the capacitance will act like a short circuit. So therefore, I should short circuit this node. Then the gain of this circuit, since it is short circuited, it behaves like a simple common source amplifier. The gain will be GMRL. So the gain increases by a factor of 1 plus GMRS. At DC it is GMRL by 1 plus GMRS. At infinite frequencies the gain is much higher, which is GMRL. So even before we look at the poles and zeros, we can clearly see that if I want to go from here, which is a lower gain value at a lower frequency, to a higher gain value, I should first encounter a 0 and then a pole at this point. And we can see the expression for 0 here is 1 by RSCS, and the expression for the pole here is actually 1 by, it's a bit more complicated, but we can make some assumptions, 1 by CS into RS parallel 1 by GM. This is the expression for the pole, and I'm going to assume GM RS to be much greater than 1. If I make this assumption, this reduces to GM by CS. RS parallel 1 by GM will be 1 by GM itself. So then that will become GM by CS. So that's what I've shown here. So the pole occurs at a much higher frequency. The 0 occurs at 1 by CS into RS. So what we can see here is that the gain increases with increasing frequency. So if you have source degeneration and if you have a capacitor at the source terminal, the effect that this capacitance has is that the gain will start increasing as a function of frequency. Now, what happens when I include CL? If I include CL, you should remember there are two poles in the system. The second pole is at 1 by CL into RL. Now, since we don't know the values of RL and CL, we'll make assumptions. We'll first assume RL CL to be greater than. So, which means this pole 1 by RL CL occurs much later than GM by CS. So, GM by CS is the low frequency pole here. So, this is 1 by CS RS is a 0. So, 0 is always occurring at the lowest value. I am assuming 1 by RLCL appears after GM by CS. So, this is how the graph looks like. The gain will flatten out when you encounter the first pole. Then when it encounters the second pole, it will start rolling off with a slope of minus 20 decibels per decade. We can also have the second condition where this pole 1 by RLCL can be lower than GM by CS. In that condition, again the transfer function will look something like this. We will first have a 0, it will increase, and when it encounters a pole, it will flatten out. When it encounters the second pole, the gain will start decaying after that. The question here is, what is the value of this peak gain here? In the previous circuit, we found out it was just GMRL, but now we'll have to analyze what is this value of peak gain here. Since we have already crossed this point, we have crossed the point of 1 by RLCL, and we have also crossed the point of 1 by RSCS, you should understand that if I have two impedances in parallel, two resistor and capacitor in parallel, RS and CS in parallel, RL and CL in parallel. So the capacitive impedance here is actually given by 1 by SCS. So as you increase omega, as you increase your frequency, the capacitive impedance will keep decreasing. At some value of S or omega, the capacitive impedance becomes equal to resistive impedance. That value is simply 1 by RSCS. So RS becomes equal to 1 by omega CS. That's the pole of this system, of this parallel RC network. So after the frequency which is 1 by RSCS, the capacitive impedance will be much lower than the resistive impedance. So when you have two elements in parallel, the one with the lowest impedance will always dominate. So here, in this case, after frequency 1 by RSCS, this parallel RC network is going to look like just a capacitor, a single capacitance of value CS. In the same way, after the frequency 1 by RLCL, this parallel RC network is also going to look like a single capacitance of value CL. So now I have a circuit which looks like this. So you have a capacitance at the source node CS and the capacitance at the drain node CL. Now the voltage gain of this circuit is given by GM by 1 plus GM ZS. That's the transconductance times the output impedance ZL of S. I'm again going to assume that GM ZS is still much greater than 1. So I'll ignore this term here. So I'll be left with GM ZL of S divided by GM ZS of S. So it will be just ratio of the load impedance by the source impedance. That gives me CS by CL. So 1 by SC, 1 by SCL by 1 by SCS, and you get CS by CL. So that's the peak value of gain here. It will be CS upon CL. So with this, our discussion on the frequency response of common source amplifiers is complete. The important points we discussed in common source amplifier is that it suffers from the problem of the Miller effect. So which is the capacitance CGD gets multiplied by a huge factor and appears as a large capacitance at the input, and that tends to reduce the bandwidth of the system. And that's a serious problem, and that needs to be addressed. The second thing we discussed about source degenerated common source amplifiers. We saw that the source degenerated capacitance, this capacitance CS here, for example, if you look at this common source amplifier, that CS can be CSB, the source to bulk capacitance. This capacitance has a very interesting effect. It increases the gain of this amplifier. As you increase the frequency, the gain of this amplifier increases. Okay, so one very important point to note here is that the main reason why we chose to go for source degeneration is to get some kind of feedback, from this source degenerated resistor. Now the parasitic capacitor here, because it's going to short it out, it's killing the feedback in the circuit. So once it shorts out, there is no feedback built in the circuit. So that's it. The next lecture, I'll discuss about the common gate amplifiers and common drain amplifier. Thank you.